Hey everybody, Professor Leach here. Today we're going to continue our journey of integrating products of powers of trig functions. The reason for this is that we want to get to the method of trigonometric substitutions. When you do a trigonometric substitution on an integral, you're going to end up having to integrate a product of powers of trig functions, either a product of powers of cosines and sines, or a product of powers of secants and tangents. That's just what falls out of the trigonometric substitution process. We want to categorize these products of powers of trig functions into pairs of P and Q that we can integrate with substitution, and pairs of P and Q that we cannot integrate by substitution. And then those are the ones that we're going to have to solve, because we really don't care in a trigonometric substitution sense about the ones that we can do substitution on. If we do trigonometric substitution and we come up with a cosine and sine or secant and tangent and we can do integration by substitution, we need to stop, go back and say, we did not need to do trigonometric substitution on this. So that's what we're finding out. We're finding out what we can do substitution on so that we're aware of it later on. Also, I mean, it's just fun, right? It's like a little mystery. Yesterday, we talked about integrals of secants and tangents. The big idea is that we have to save something to be the dw and then substitute the rest. That's what's going on in these integrating products of powers of trig functions. We need to save something to be the dw and then convert the rest. The convert the rest part comes through the Pythagorean identities. So converting the rest only works in pairs. So to recall, if we make the substitution w equals tangent x, then dw is secant squared. So if I want to make the substitution w equals tangent x, I need at least 2 factors of secant to be the dw. That's the way that we think about it. We need 2 factors of secant to be the dw. Then we would convert the rest. Then we would convert the rest of the secants into tangents. And so secant squared is 1 plus tangent squared. But when we convert the rest have to convert in pairs. So convert the rest only works in pairs. So that's why we need P to be even. We need an even power of secants to make tangent the substitution. I need 2 of them, 2 factors to be secant, 2 factors of secant to be the dw. And then I need the rest to come in pairs so that I don't end up with square roots. Because I want to convert a secant to the third of x and have the square root of 1 plus tangent squared. That would be a secant to the first. I don't want a secant to the third of x to have 1 plus tangent squared x all to the 3/2 power. We're introducing radicals. Radicals introduce complications. Trigonometric substitution is supposed to get us out of those kinds of situations. So the rest convert in pairs. That was the way. So it's convert the rest in pairs. Pairs are really things that are added together, but that's the even number part that I need. So if P is even and Q can be anything it wants, then dw is secant squared, and then the rest of the secant squareds can be 1 plus tangent squareds, which will become 1 plus w squareds when we make the substitution. So we've taken care of P is even because Q can be anything it wants. Even if Q is 0, even if we don't see any tangents at all, we still want to make the substitution w equals tangent. So that's kind of interesting. That's kind of a fun trick. So here's the new, one of your classmates has made a discovery in the discussions, if P is odd, and this is the big part, and Q is also odd, then we can make the substitution secant. Let's talk our way through this and convince us that this is true, and then grab an example and run through it. So the claim is if P is odd and Q is also odd, then we can make the substitution secant x. The reason that Q and P both need to be odd, actually, Q is the one that really needs to be odd in this scenario. The reason that Q needs to be odd is the form of dw. dw in this case is a secant x tangent x, because the derivative of secant x is secant x tangent x dx. So this means I need one factor of tangent to be the dw. So I've taken an odd power of tangent. One factor can be is going to contribute to the dw. That'll leave an even number of even power of tangents left over. Then we can convert the rest. So then we can say that tangent squared is secant squared minus 1. So we start with an odd number of tangents. We save we put one aside to be the dw, and then there's an even number left that we can convert. So this is what we can do if P is odd. I said this is what we can do because this is not our only option, but it fits with the trajectory of how we're studying this. So my follow-up question on the discussion is going to be, oh, is this the only thing that we can do? And then the student response is going to be like, oh, you have to have the annoyed sigh, because he's just it's like when the teacher, the teacher's going to ask, explain, and you have to like start writing sentences in your math class, and so you're like, well, that's annoying. Let's grab an example where P is odd. So I'm going to have an odd power of secants. Let's have an odd power of secants and an odd power of tangents. With an odd power of secants, and an odd power of tangents, I need both of those things. I should have emphasized this and more. That's when we can make the substitution W equals secant x, and dw in that case is going to be secant x tangent x. And then we'll be able to convert the rest through tangent. So tangent squared x will be secant x, or secant squared x minus 1. I'll write that one in the orange because those are going to get turned into w. So the tangent squareds will become w squared minus 1. Because that's what we're going for, a polynomial in w. So here's how this is going to break down. The secants are all going to be, one of the secants is going to contribute to the dw. There's going to be two secants that are going to form a w squared. So the way that we're breaking this down is that we have one factor of a secant to be the dw. That leaves two behind. So there's going to be a secant squared It's going to be two factors of secant squared that'll show up as the w. I need one factor of a secant and one factor of tangent to be the dw. And then I had 5 tangents, so there are 4 tangents left over. And so this is how we're looking at, oops, maybe I should do this to call it out. So I'm splitting up the secants to one secant. I'm saving one secant to be the dw and one tangent to be the dw. Now I can make the substitution w equals secant, and I have an even power of tangent that I can convert. So tangent to the fourth is going to be a tangent squared x squared. So this is going to be a tangent squared x all squared. And tangent squared is going to be secant squared minus 1. And this is useful because secant is what we're replacing with w. So now we can make all of our substitutions, and we can get an integral in w. So the substituted integral will look like the integral of w squared, and then we'll have secant squared x minus 1 squared. Secant is w. And then the secant x, tangent x, and the dx all become dw. And that's what we wanted. An integral in w only. Everything is accounted for. All the powers of secant and all the powers of tangent. So really, this is the case where P is odd and Q is also odd. What really needs to happen is that if we want to make the substitution W equals secant, we just need to save one factor of secant and one factor of tangent. What we really need is that one factor of tangent. So notice that in this case, P can be anything, and we can make the substitution. As long as we got one factor of tangent to be the dw, and an even number will be left over, then P can be anything it wants. Even if we had a secant to the 1/2 power, tangent to the 5th, we could still do that. We could still make the substitution secant x. Any questions? So notice that P can really be anything it wants as long as Q is strictly odd, integer and odd, because one of the tangents can be needs to be saved for the dw. Then we'll have an even number of tangents left that we can convert into secants, which become the w. So that's an important thing to note. So in this case, P can be anything we want it to be. So for example, we're going to have to get clever with our powers. But if we had, say, let me write a weird one. Let's say we had tangent to the 5th x and say the square root of secant x dx. Right now, you should be thinking, now you're just making stuff up, Leach. I'm like, oh yeah, that's the whole point. We're going to see where this works. So in this case, this might even call us out to do secant because it's in that square root. If I make the substitution, w equals secant x, and that would require a dw of secant x tangent x. And then the tangent squareds, this is the restriction. The tangent squareds will become secant squared minus 1. That's the real restriction. Saving things for dw, we have a secant to the 1/2 power, and I need a full secant of x to be the dw. So I'm going to subtract 1 secant from this 1/2 power. And I'm going to read this as a tangent to the 4th I'm going to split this secant to the 1/2 power into a secant to the negative 1/2 power. I didn't leave myself enough space. A secant to the negative 1/2 power, because if I combine a secant to the negative 1/2 power with the secant to the 1 power, 1 minus a half is a half. So now I've got everything accounted for. I've got a secant x tangent x dx to be the dw. I've got an even power of tangents that we can convert, and this part is just going to show up as a w to the negative 1/2. And since we're aiming for not quite a polynomial, but this will still result in a bunch of powers of w. So you do some stuff in the middle, and you're integrating tangent to the 4th is going to end up looking like w squared minus 1 squared. Secant to the negative 1/2 is going to be a w to the negative 1/2. And all this will become dw. This is still better because we could just multiply all this out. This is a w to the 4th minus 2w squared plus 1, and then we just distribute the w to the minus 1/2. So inside, we have a w to the 4th, gonna run out of space, minus 2w squared plus 1, if we just multiply that out, and then we'll distribute the w to the negative 1/2. So I'll have w to the 3 halves, wait, no, 4 halves, 4 is 8 halves, so 8 minus 1 is 7, right? Go with that for now. Minus 2, w to the 4 minus 1 is 3 halves, plus w to the negative 1/2 dw. So really, the q is odd thing is what's telling us to do the secant x as a substitution.
Sorry, how did you get w to the 7 halves?
I took w to the 4th and multiplied by w to the negative 1/2.
Oh,
4 is 8 halves, minus a half is a 7 halves.
Got it, thank you.
So really, the restriction comes down to converting the rest in pairs. That was the big thing. Saving something for the dw, we can be flexible with that because w is very easy to substitute. It's converting the other ones. If we make w equals secant, getting everything else to look like secant, that's the trick. That requires the pairs. Any questions? So what we're trying to avoid is square roots of more than one term. That's what we want to try to avoid. That's the big avoidance that's going on here. We're trying to avoid square roots of more than one term. We're trying to avoid, I'm going to smear all my ink. Oh, it's going to be terrible. Try to avoid square roots of more than one term. If we just have the square root of one term, no problem. I can just write that as w to the negative 1/2. But if we have the square root of more than one term, then we have what's known professionally as a mess. So square root of x, good. Square root of x plus 1, bad. I haven't particularly justified this particular problem, but trust me, it's a problem. Any questions? Comments? Deep thoughts? Let me take a detour into this square roots of more than one term bad by looking at, yeah, let's just take a look at this. Let's suppose that we wanted to integrate see, my dog doesn't even like it. So let's take a look at the integral. Let's go with x over the square root of 1 minus x, the x. I doubled up on the complications. I think this is page 2. So the integrals that we've seen so far, if there's one term in the denominator, we can just distribute that to the numerator and break into terms of x. If we just have one term in the denominator, we can just use the distributive property and distribute it to the numerator. If we have one term in the denominator, if we have only one term in the denominator, then we can use the distributive property to the numerator. Oops. And we've done that before. We had a quiz where it was everything was over x squared. You just divided all the terms by x squared to get terms in x. But we can't do that here. First of all, there's only one term. And the square root of the terms is in the denominator. So we just have to be sneaky. I'm going to make a substitution. I'm going to substitute w is equal to 1 minus x. I have to substitute dw is just going to be minus 1 times dx. So a minus dw is going to be the dx. Now this takes care of the square root of 1 minus x, and it takes care of the dx, but now I've got this x in the numerator that I also have to deal with. So we've taken care of a lot of stuff here. This is going to be the square root of 1 minus x is getting replaced with w. The dx is a minus dw. But we also need to replace the x up in the numerator. Fortunately for our heroes, we have a way to replace the x in the numerator. I can take this expression w equals 1 minus x and I can solve it for x. So this tells me that x is equal to 1 minus w. This in the products of powers of trig functions would be the maneuver where we replace all the tangents with secants. So I'm going to replace the numerator with 1 minus w. We still have a fraction, we still have the radical in the denominator, but we have made big progress because now we only have one term in the denominator and we can use the distributive property and move it up to the numerator. Now I just have all this stuff multiplied by w to the negative 1/2. So now I can rewrite this as powers of w. I'm going to distribute the negative. W divided by w is a w to the 1/2 power. minus 1 over the square root of w, which is a w to the minus 1/2 power, dw. So I distributed the negative and wrote them in the other order. So that x equals 1 minus w, that's like when we were doing products of powers of trig functions and replacing the tangents with secant squared, tangent squared with secant squared minus 1, or replacing secant squared with 1 plus tangent squared. Because now we have terms that are all just powers of w. Now we don't have now we have one term in the denominator. And here's the way that we got it. We want to try to get to a place where we can just use the distributive property. Any questions?
So is it now just the integral of 0?
No. 1/2, a w to the 1/2, and the other w is to the minus 1/2. They're not like terms.
Gotcha.
So when we add 1 to the exponent, 1/2 plus 1 is 3 halves. And so we divide, so we get 2/3 w to 3 halves. Minus 1/2 plus 1 is 1/2. And we divide by 1/2 to get a coefficient of 2. And then we can replace the w's. Even though the problem was presented with radicals, I'm going to write my answer with fraction exponents, because otherwise I'd have the 3 halves here. I'd have to write that as a 1 minus x times a square root of 1 minus x to write this as a square root of 1 minus x. So I'd have to write this as a square root of 1 minus x cubed, which is not simplified. I have to pull out that 1 minus x and leave a square root of 1 minus x. Then I should be factoring out the square root of 1 minus x anyway. So I'm just going to leave it like this, because leaving the answer like this clearly demonstrates where I got the answer from. But if you're going to see this in some computerized fashion, then maybe we factor out the 2/3 and the 1 minus x to the 1/2 power, because that will leave behind a polynomial. So from a style guide perspective, we might want to factor out the fraction part and a 1 minus x to the 1/2 power. That will leave a 1 minus x to the 1 power. And then 2 divided by 2/3 is, I can't do it, times 3 halves, right? Oops. So 3, is that going to be a 3? That's arithmetic. I'm not very good at arithmetic. 2/3 times 3 is 2. Oh yeah, the 3's canceled, duh. I'm not good at arithmetic, so if you're going to start simplifying things, then maybe this would be the form that you would want to write it in, but I would just leave it, because right now we're doing algebra, and every time we just start doing algebra that's not really necessary, that I've explicitly stated is not quite necessary. Oh, look at this, minus x minus 2. Once we start doing optional algebra, we start taking risks that are too great, because who knows if I did my arithmetic correctly. Right. Any questions? This is also, but it's useful to be able to do these kinds of things. Maybe when you're writing, typing your answers for the quiz, you want to just leave it here, because that's perfectly acceptable. But if all you write is something like this, I'm not sure what Wolfram alpha would deliver as the antiderivative. But if you write nothing and just copy and paste from Wolfram alpha, I want you to first of all recognize that it is super obvious when you just copied and pasted your answer. I can see that. It's just blatantly obvious. I can also see if you just typed what you saw on Wolfram alpha. So Don't think you're fooling anyone. Don't worry about me saying something, because if that's the way that you want to go through life, then, I mean, what am I going to do? Try and stop you? But don't think, he didn't notice. I totally noticed. Even though we're separated by this computer screen, I don't have to be in the physical presence of the person to tell when they're lying to me. Student. I always know when students are lying to me. I'm not saying don't try it, because there are certain times it's going to be totally acceptable. You're going to send me an email and be like, oh, Leach, I'm so sick. I can't go to class today. And they go, oh man, that's terrible. Feel better. And you're like, oh, that worked. Yeah, because you can just like stay home. You don't have to actually be sick. You could just be sick and tired of hearing me. So take a day. You know what I mean? Take care of your mental health. So we have made some progress. There is something that's left out though. We've made progress on our secants and tangents, and we also need to deal with cosines and sines. So we can deal with P even and Q any. We know that we can make a substitution of W equals tangent X. If P is anything and Q is odd, then we can make the substitution W equals secant X. So we can deal with P being even and Q being odd, but this does not hit all the combinations. What if P is odd and Q is even? That's something we have to deal with. What if P is odd and Q is even? That's on the list of things that we didn't do. And also, let's see. No, that's pretty much it. We got to deal with odd powers of P and even powers of Q. What this boils down to, odd powers of P with even powers of Q, since even powers of tangent can become even powers of secant, odd powers of P and even powers of Q, this just means odd powers of secant. So this last one is equivalent to odd powers of secant. Odd powers of secant paired with even powers of tangent just means odd powers of secant. That's going in the discussion as well. Why can I say this? And we need to deal with the cosine and the sine. Any questions? So I'm going to expand the discussion since we have dealt with the odd powers of secant paired with odd powers of tangents. Now we need to go up to odd powers of secant and even powers of tangent. And we also need to deal with odds and evens, cosines and sines. Any questions? Comments? Deep thoughts? All right, that's your project for the weekend. Deal with odd powers of secants explain why odd powers of secant means P is odd and Q is even. Because what if Q is 4? There's tangents there. Why am I just ignoring the tangents? So what I mean is, like, why don't I have to bring up the tangents? And then start dealing with what substitutions can we make with cosine and sine with P and Q, because it's set up a little bit differently over there.
Is that the integrating secants and tangents assignment?
Yes. So I'm
Got it.
going to expand the integrating secants and tangents to, I'm going to go retcon that one into being integrating products of powers of trig functions. I just wanted it focused when it first came out.
Got it.
All right. That's going to do it for today. That's going to do it for this week. Y'all have a nice weekend. Thanks for playing. Peace out.